All right, so thanks everyone for tuning in. Welcome to the first Quantum Gravity and Information Seminar of 2020. Today we're very happy to have Douglas Stanford, who's going to tell us about replica wormholes and the black hole interior. Douglas, thank you very much, and take it away.
Okay, yeah, thanks for the opportunity to do this. I'm not sure exactly how well it's going to go because I'm a little sick, and it's also quite early, but we'll see. And I think it will help if you guys ask questions. And the amount of material I plan to discuss is less than an hour, so there's plenty of time to have questions and discussion. So what I'm going to be talking about is based on a recent paper with Jeff Pennington, Steve Schenker, and Zhenbin Yang. And our paper was motivated by some beautiful work from last spring that was done by Pennington, Amiri, Engelhardt, Marolf, and Maxfield on the page curve. And there was some important follow-up work in that topic by Amiri, Mahajan, Malasena, and Zhao. So our work is continuing along that line. So the motivation is this work I mentioned on reproducing the page curve of an evaporating black hole using essentially a holographic entanglement entropy computation. So like a souped up version of the Ryu-Takayanagi formula. So let me just review what that situation is. This is a diagram, or cartoon, of a Penrose diagram for an evaporating black hole in flat space-time. These lines, I don't know how visible they are, these wiggly lines are representing Hawking quanta. So the ones outside the horizon, the ones over here, represent the radiation that leaves the region of the black hole and approaches a region where there's where gravity is essentially unimportant, out near Scribe Plus. And the other sides of these lines represent entanglement between those quanta and the interior partners of the Hawking quanta. In the Hawking process, there's entanglement between some modes behind the horizon that fall into the singularity. Those are these ones. And the modes outside the horizon that become the actual physical Hawking radiation. That's these. And the naive formula for the entropy of the Hawking radiation, discussed by Hawking himself, is just thermal entropy for all of the physical Hawking radiation that comes out. So we're going to use parameter k to describe this, where k labels the number of different states of the Hawking radiation that we've had so far. So suppose the black hole has evaporated for a while, up to some time, right, looking at some time slice like this. Then we look at the amount of Hawking radiation on this time slice outside the black hole, and we count the number of possible different states of the Hawking radiation, and we call that k. So the entropy would, roughly speaking, be, the thermal distribution would be log of k, and that would just increase as the amount of Hawking quanta increases and increases. But this runs into a contradiction with the fact that the black hole itself is expected to, can't be entangled with more than its own entropy worth of Hawking radiation. So the proposed corrected formula proposed by Page is roughly that the entropy of the Hawking radiation should be the minimum of two terms. The first one is the naive term, the thermal entropy of the Hawking radiation, log k. And the second term is the Bekenstein-Hawking entropy of the remaining black hole. So area divided by 4 g-Newton of the remaining black hole. So this formula, the minimum of these two terms, is known as the Page curve. For an evaporating black hole, it will rise. This will rise linearly for a while as the amount of Hawking radiation increases, and then it will decrease as the black hole evaporates down to zero size. Okay, And it was a mystery how to reproduce this formula from the perspective of bulk physics for a long time. And this spring, it was shown how to reproduce this page curve formula using the island conjecture, or island formula, which is a rule that was proposed for the computation of holographic entanglement entropy, like a rule that you should use when applying the Ryu-Takayanagi formula to this situation. So the goal in our paper from this fall was to derive this rule from the gravitational path integral and to try to understand in some more detail why the formula is correct. And well, in our paper we give a sort of a more general argument, but I'm going to go through just a part of the paper which deals with a very simple model of a situation similar to this one, where you can compute the entropy using the gravitational path integral, and things are a little bit easier to understand. Okay, are there any questions about the motivation or setup, or questions about the literature on this topic from the spring?
No, we're good here. Thanks.
Has there been a talk about the island formula in this?
Not so far, no.
Okay.
Again, if you want to ask a question, feel free to just unmute your mic and speak up.
Yeah, I think this probably won't work very well unless people ask questions. So really, please do ask questions. Okay. Well, so I'm going to start introducing the model that we studied, and then we'll analyze the entropy in that model. So this is a JT gravity plus end of the world brains model. JT gravity is a simple two-dimensional theory of gravity. It has some action I, JT. And the action for the combined model is the JT gravity action plus the term for the end of the world brains. And the way that works is we have two-dimensional gravity. The end of the world brain is some codimension 1, so it's a one-dimensional locus, so it looks like the world line of a particle. And the action associated to it is just some parameter mu times the total world line length. So we can draw some classical solutions of this theory of JT gravity and the end of the world brain. So first, let's look at the one on the left. This is a classical solution in Euclidean signature. So JT gravity without end of the world brains is a two-dimensional theory of gravity that describes negatively curved spaces. So the classical solutions are hyperbolic space or quotients of hyperbolic space. And here I'm representing the hyperbolic space using the disk model, the hyperbolic disk. And the difference is in the model with the end of the world brain, you can have only a portion of the disk, a portion that's cut out by the world line of the end of the world brain, which is propagating along here. And because of this action term here, the end of the world brain likes to propagate along a geodesic, the same as a massive particle. So the classical solution consists of a portion of the hyperbolic disk, which has been cut out by a geodesic. So the region is topologically a disk, and it has two parts to the boundary. One is the end of the world brain, and the other is the asymptotically ADS boundary up here. Okay, so this is in Euclidean signature. And one thing to note is that to emphasize is the end of the world brain intersects the boundary at these 2 points, this point and that point. Okay, so let's now go to, I haven't explained why this model is related to the evaporating black hole or anything yet. That will come in a second. Let's go to Lorentzian signature. In Lorentzian signature, we can take this geometry here and analytically continue it. And a way to think about that is you take this slice here, this t=0 slice, and you put that slice here as a t=0 slice in Lorentzian geometry. And then you go forwards and backwards in time with Lorentzian evolution instead of Euclidean evolution. If you do that, you end up with a Penrose diagram that looks something like this. We have an asymptotically ABS boundary over here. And we have the end of the world brane over here. You can see that the end of the world brane is behind the horizon of a black hole. So this is, these lines here are the horizons of a black hole. The bifurcation surface is at this location here. And the end of the world brane is propagating behind the horizon of the black hole. So similar geometries were discussed earlier, including in a paper by Korkulu and Maldacena.
I'm sorry, can I ask a naive question? Maybe I missed it, but can I see the black hole in the Euclidean signature at all, or where was that diagram?
Well, no, it's like to discover that there's a horizon there, you should really continue to Lorentzian signature. It's the same as for the Euclidean, the standard Euclidean black hole is like, it's like this cigar geometry or a disk. And the horizon is at one point in that Euclidean geometry, which would be this point here. This point here is the same as that point, and that's the bifurcation surface where the two horizons meet. But to tell that it's a horizon, it's simplest to continue to Lorentzian signature.
Did you have to put it behind the horizon, or could you arrange it for it to be outside the black hole, the end of the world brane?
You could have it outside. I think you could have it outside the horizon. Then it would be like some brane that would fall across the horizon into the black hole. So that would be like a slightly different setup.
Thanks.
I'm not 100% sure, but I don't see any reason why you couldn't have it. There may be a reason why you can't have it, but I don't see it at the moment.
Okay.
Actually, well, it might be in that case it needs to have negative tension. I'm not 100% sure about that.
Okay, I'm just curious.
But in general, you could have a geometry like that where something outside the horizon falls in and thermalizes a form of black hole. Okay, so to make this look a little bit like the evaporating black hole, what we're going to do is...
Question.
Yes, sorry, go ahead.
This is Laurus Tamasils in Reykjavik. Usually when you have a Euclidean geometry, you only see things that are outside the black hole horizon in the geometry, in the Euclidean section of the geometry. But here that seems to be different. This end of the world brane seems to be visible in the Euclidean geometry.
Well, I'm not sure why you say that, though.
But just take a Schwarzschild black hole, the Euclidean geometry is entire, it only covers the outside of the horizon.
Well, not quite. Like so the Euclidean geometry for the Schwarzschild black hole is this cigar, right? And it has, so the cigar, let's show the cigar here.
That's a bit too low for us. I don't know about other people. Oh, there we go, thanks.
The cigar here. Then the horizon would be at this point, and the part of space outside the horizon is over here. And on the other side of the cigar is the part behind the horizon.
Is it?
So this looks like that looks like this line here that goes clean across. The Euclidean geometry contains things that are on the other side of the black hole as well. And that's sort of like what this end of the world brane is doing it. At t equals 0, it's sort of like it's in part of a second asymptotic region. Then it falls into the singularity. Does that answer the question?
Well, it answered the question, but I'm not sure I'm happy with the answer.
Could you ask a follow-up or something?
Anyway, keep going. We can return to it at the end.
Okay. Well, so the idea behind putting these branes here is that the brane behind the horizon is going to mock up the interior partners of the Hawking radiation over here. So one way of phrasing the puzzle about the evaporating black hole is that naively, you get a huge amount of entanglement between the Hawking radiation outside the black hole and the interior partners behind the horizon. And the problem is, in some sense, that it looks like you can put too many different orthogonal states behind the horizon of the black hole. There are too many different states that the Hawking radiation can be entangled with, too many states of the interior partners that the physical Hawking radiation outside can be entangled with. So to come up with a model where we have lots of possible states behind the horizon mopping up those interior partners, we'll give this brain flavor index I, and we'll let I run from 1 up to k. And we'll imagine that k becomes very large, comparable to exponential of the entropy of the black hole. So instead of having actual propagating quantum fields and Hawking radiation on the background, we're just going to have this end of the world brain behind the horizon and allow it to have a very large number of possible internal states. Okay. So the state of the whole system that we're going to consider to mock up this evaporating black hole is the following. We take a state of, it's a sum over k terms, where psi I here represents the state of the black hole, where the end of the world brain is in state I. So that's roughly this picture here. And this extra system I, R, is a reference system that we've entangled with this state of the black hole. So you should think of the reference system as being like the physical Hawking radiation outside the black hole in some essentially non-gravitating region. And that system is entangled with the choice of state of the end of the world brain. So just like for the evaporating black hole, the physical Hawking radiation is entangled with a choice of state of the interior partners. Here, the model for the radiation, the system R, is entangled with the choice of the end of the world brain behind the horizon. Okay, and basically what we would like to find in this model is we would like to find this formula. We would like to find that the entropy is the minimum of log k and S Bekenstein-Hawking. That's the island formula of the papers that I mentioned at the beginning of the talk. So we would like to understand why that's true in this simple model. Okay, any more questions at this point? Move this over. Okay, so as a first step, basically what we're going to do now is we're going to compute the entropy of the system R. And we're going to see if we can get this formula, the minimum of log k and S Bekenstein-Hawking. So let's take a first pass at computing the entropy by first computing the density matrix of the system R. So to compute the density matrix of system R, we take the full state of the system, that's this psi here, and we trace out the black hole B to get a density matrix just in the radiation system R. And the result of that computation is this formula here. The matrix elements of the density matrix are given by these inner products between states where the black hole has an end of the world brain in state I versus end of the world brain in state J. So to compute the density matrix, we need to understand what these inner products look like. And they're defined by a boundary conditions for a gravitational path integral. The way this works is as follows. First, let's define unnormalized versions of these states, and we'll normalize them minimally. So the tilde here means an unnormalized version. The boundary conditions that compute a inner product between the black hole with end of the world brain in state I and state J are sketched here. What this diagram means is the following. The solid line here represents a patch of asymptotically ADS boundary of a given length, but with a shape that is not determined. And the two dashed lines are supposed to enforce that some end-of-the-world brane of type I should intersect the boundary at this point, and an end-of-the-world brane of type J should intersect the boundary at this point. So we'll have some Euclidean computation where we have a segment of asymptotically ADS boundary, and the two end-of-the-world branes will intersect it. One has type I, one has type J. Those are a complete specification of the boundary conditions to compute this quantity. So we should take these boundary conditions and try to find a two-dimensional gravity configuration that fills them in. And one that does so is just the Euclidean geometry we had a moment ago with the diagram rotated. So the shaded region is two-dimensional hyperbolic space, and one component of the boundary corresponds to an end-of-the-world brane, which intersects the asymptotically ADS boundary in two locations. Notice the following. At these two locations, we need to have an end-of-the-world brane of type I intersecting here, and an end-of-the-world brane of type J intersecting here. But in the bulk, it's the same end-of-the-world brane that connects the two together. So that means that the amplitude should be proportional to delta ij, Kronecker delta ij, with some factor z1 that is the gravity path integral on this space here. And z1 will just be the normalization of this state, psi tilde, so we should divide by it to compute the inner product of the states psi. So, so we conclude from this that the rho r is going to be...
That's a bit below the bottom of the screen.
Okay, yeah, thanks. Let me tilt it down.
Perfect.
You see?
Thanks.
Okay, 1 over k times sum over I of so it looks like just a maximally mixed state on the k different possible states of the reference system, the radiation. This is analogous to Hawking's calculation, where he found that the state of the physical Hawking radiation is thermal. In this model, we would find that the state of the reference system, the radiation system, looks like it's just a maximally mixed density matrix with entropy log of k. So we sort of failed at reproducing the formula that we wanted to find, which was the minimum of log k and S. Bekenstein Hawking. We wanted to find this formula, but instead what we found was just log k. And that's actually the this version of the black hole information problem, the entropy problem, is that if we make k very, very large, then it looks like the entropy can be far bigger . Move back over here and erase this part of the board. Any questions while I'm erasing this?
Sorry, our video feed here in Potsdam froze. Could you repeat maybe the last 60 seconds?
Oh no, it froze?
I don't know if it was everyone or just us, but we missed the last maybe 60 seconds. Could you just...
Oh, sorry about that. What was the most recent thing that you heard?
You had basically it's purified by these, instead of, normally I would say the external radiation is purified by the black hole, and now it's purified by these states log k on this end of the world brane, and you can make k as large as you like, which is the paradox, and that was basically where this last thing I remember.
Okay, well, right, so the problem is that the entropy of the reference system R can get too big, which means that the entropy of the black hole is bigger than its coarse-grained entropy.
Right.
And that's the problem that this island and the gravitational path integral. So what we're going to do now is entropy directly. So as a first step, let's compute what's called the purity, trace rho squared. If we put this maximally mixed density matrix that we computed a moment ago into this formula, trace rho squared, then we'll find the answer 1 over k. And the analog of the entropy getting very big over k can be made arbitrarily small by making k very, very large. And the thing that we would like to find is that the purity can't get too small, can't get smaller than e to the minus the entropy of the black hole. So let's directly try to compute trace rho squared. So if you start with the formula for rho over here, and this formula for rho, then you find trace rho squared is equal to 1 over k squared sum over I and j of psi I following. Where we have two segments of asymptotically ADS boundary that intersect into the world brains, I and j here. I and j here, where the arrows look like this on the boundary, going from ket to bra. So these are the boundary conditions. They look like two copies of the boundary conditions that we had a moment ago. We'd like to see how they can be filled in with two-dimensional geometry. So one way to fill them in is to just do two copies of what we did before. So I'm going to draw two different terms that can contribute here. One term that can contribute is this thing. And then another thing that can contribute is a connected geometry. Okay, so here are the two geometries that can contribute to this quantity. One is just two disconnected copies of the previous computation. That's clearly going to be proportional to Kronecker delta ij. The other geometry that can contribute is one where we have one connected geometry, where these boundaries ones here curving inwards are the end of the world brains. And if you look at this diagram, you'll notice that now the same so that diagram is non-zero for any value I and j. And when we continue to compute this purity trace rho squared, we're going to find that this thing is equal to 1 over k squared times, let's evaluate the first diagram. Sorry, I should put 1 over k times z1 squared to normalize the state correctly. The first diagram gives us one factor of k because we inserted a Kronecker delta ij, so the two sums collapse to a single sum. We get a k times the path integral on two of these half moons, that's two factors of z1. And the second term here, this one.
We can't quite see what you're writing there.
Okay.
Perfect. Thanks.
Thanks. So this quantity is 1 over k plus z2 over z1 for the purity trace rho squared. So let's try to analyze this answer a little bit. To answer 1 over k is what we would have got from the maximally mixed density matrix. And so we get that term here that comes from this trivial geometry where we have just two disconnected copies of the computation for the density matrix itself. The novel thing is this additional term here, z2 divided by z1 squared. It's independent of k, and it's just given by a gravity computation. In principle, to compute it, we have to do the path integral on this connected space here, and compare the path integral on this space here to the path integral on these spaces here. And sorry, go ahead.
The internet has been a bit choppy.
Is my connection not good? Hello? Hello?
We can still hear you. Ours has been glitching out, but the institute here sometimes has problems with that. Are other people having trouble with the pause the recording? Okay, go ahead.
Did you hear what was the most recent thing that you heard?
In Potsdam, we heard you explaining that to get this new term, you need the difference in path integrals in the second piece and the disconnect.
The ratio of the path integrals on these two spaces, and that can be computed exactly in JT gravity, but it's enough to kind of see the, well, let me not go too much into the details of that. That's a straightforward computation in JT gravity, and you find that this thing is, roughly speaking, this is e to the minus s well, some e to the minus s like quantity for the black hole. So the answer looks like 1 over k plus something like e to the minus s of the black hole. Notice that the second term, the e to the minus s term, is independent of k. So if we make k extremely ridiculously large, that's the region where we're going to be getting into trouble. If we make k extremely ridiculously large, then this term will be unimportant, and the whole answer will come from this second term. And that second term will give us something which is reasonable for the black hole, something like the purity trace rho squared is like e to the minus s. So this is the basic mechanism from the gravitational path integral perspective of how this overfilling problem is resolved. The overfilling problem of the black hole is resolved. And it's the basic origin of the page curve. That when you go to compute trace of rho squared, trace rho to the n, there can be connected geometries that contribute, connecting the different replicas together. These are what are known as replica wormholes. And they lead to contributions to the entropy that don't get smaller. Contributions to the entropy that don't grow as k increases, or contributions to the purity that don't get smaller as k increases. And so far we've just discussed the computation of the purity trace rho squared. I'll show you in a moment on some slides the computation of the von Neumann entropy.
Can I ask a question? Sorry. Are there other contributions to the purity, like connected geometries with handles? And if yes, like, are they suppressed by what factor?
Yeah, so there will be contributions like that, and those will be further suppressed by factors of e to the minus s black hole. So, and they won't be like growing with k. So those will be contributions that are uniformly ignorable. So for this calculation that I showed here to be exactly correct, it's exactly correct in a limit where k is much bigger than 1, e to the s black hole is much bigger than 1, but with k over e to the s black hole fixed. So in this limit, these two terms are comparable to each other, so we can't drop one or the other. But the further terms associated to handles that you were describing would be suppressed by further powers of this large parameter and will be ignorable. But it's a good question, and in general, those contributions will be there. Okay, so there's a perspective on this that I think is interesting, which is to try to dig a little bit into the computation and understand why we're getting this answer for trace row squared and some of these two terms. And in particular, how this formula can be consistent with our previous computation of the density matrix, right? Before we just computed the density matrix and we found that it was maximally mixed. A maximally mixed density matrix will have purity 1 over k. So how are we getting this 1 over k plus this other term? Where is this other term coming from? And it can be traced to the following sort of weird fact, that the gravitational path integral predicts that this inner product is delta ij, but its square is delta ij plus z2 over z1 squared. So what we're computing, sorry to move this again, but what we're computing in this drawing here is really just the second line here, the square of this inner product. And the two terms here contribute delta ij plus z2 over z1 squared. So it looks like when you ask gravity, what is the answer for this inner product? It tells you, oh, that's delta ij. And that's why we computed the maximally mixed density matrix that we found before. But if you ask gravity, what's the square of that inner product? It tells you it's not delta ij, it's delta ij plus a correction. It's non-zero even if I is not equal to j. So this is sort of a funny state of affairs where it looks like the path integral gives you inconsistent answers for these two quantities, right? This thing should just be the square of that thing, but it's not in this computation. And one way of trying to interpret that is to say that the gravity path integral is computing an ensemble average of quantum mechanical inner products, not inner products literally. And that's something that we've been discussing in this KITP program that's happening right now, and it's a fairly confused state of affairs. I think it's fair to say that it's not clear what the right way to think about this is here, whether we need to invoke some kind of an ensemble or whether we don't. And I think it's an interesting thing to think about some more.
Okay, I have a question there. So you said that we need the second term in the psi I, psi j squared computation, because that's what gives us the correct stage curve. In other contexts where we get a wormhole, we get a connection between disconnected geometries in the ensemble average computation, that should go away when I consider a specific instance. Like if I do the Z beta 1, Z beta 2 computation, yeah, that's got a non-zero connected component in the ensemble average, but in a particular instance, that should actually be 0.
Yes.
So, but here we want to say that it's really the second line that's telling us the right thing.
Yeah.
So do you have any insight into when the connected things are capturing the correct physics and when there's something that's just a property of the averaging?
Yeah, this is a wonderful question, and something that we've thought about quite a lot. And so I don't have a perfect understanding, but let me say a couple of things. So one thing is that suppose we have a fixed instance.
Mm-hmm.
There's no ensemble average. Then instead of these answers, you would expect that the first line should be delta ij plus some tiny correction. Some erratic but small correction. And the second line, we would have a term with the square of this thing.
Right.
Now, what you'd like to do is interpret the second term here as being the variance of this erratic correction. And you can think about that as being the variance in some kind of ensemble that's implicit in the gravity description. Or you could think about it in the computation of the Renyi entropy of the purity as the variance over the ensemble defined by different INJs. So in the computation of the purity, trace rho squared, we're summing over a lot of terms, INJ. And you could imagine that this term here is the right answer for the average over INJ, not over some ensemble of theories. So in other words, in the computation of the purity, there's some kind of ensemble there that's just the lots of different states. It isn't an ensemble of theories. So you could imagine that in the computation of the purity, even in a fixed theory, this term here gives the right answer.
Variance.
Now, you should then kind of worry, like, okay, so how am I supposed to know that in a fixed theory, I can use this formula if I'm trying to compute the purity, but I can't use it if I'm trying to compute just the inner product of these states, just one of them, like fixed INJ. Because for fixed INJ, this should be some erratic thing, square Rij. There's no ensemble for fixed INJ. And I think, well, we don't have a good understanding of this, but a kind of rule that you could use as a diagnostic is you could try to compute in gravity, you could try to compute this quantity, and you could try to compute the square of this quantity. You could try to compute, so let me draw another thing. We could draw this thing square. That would be this thing to the fourth power. And if we do that, we'll find additional connected geometries that we can have, and it won't be consistent with just this one. So we'll find that within the gravity approximation, that this can't be right for fixed INJ, because it is the computation of the square of that. So a diagnostic is, if you're not sure if something is accurately computed by the wormholes, then try to compute its variance using wormholes. If the variance is small, then maybe you should trust the computation, and if the variance is large, maybe you shouldn't.
Okay, that makes sense.
I should mention that a more optimistic scenario, something I hope is true, but I don't know if it's true or not, is that if we were to study like a more interesting gravity theory, more interesting than JT gravity plus end of the world brains, you know, maybe it's the case that there's something wrong with this computation. That it's okay when you compute the purity, but when you compute this quantity itself, there's some problem that arises in the bulk computation that warns you that you shouldn't take the wormhole seriously. And I don't know what that would be, but that would be the best case.
Okay, thanks.
Okay, I think I'm going to move to the slides now, but are there any questions about the stuff that we've discussed so far? Any more questions? Okay, so then let me move to the slides. So I hope this is visible. Let's see, how can I? Is that visible?
It was visible before, and now we're just seeing a black screen.
Okay. Oh boy. How about that?
That's visible, and we can see your pointer, so you can use that to
Just stick with this then. Okay, so so far we considered the boundary conditions for computing trace of rho squared, and we saw there were these two terms. If you want to compute the von Neumann entropy, rather than the Renyi entropy, or the purity, trace row squared, then what you need to do is, well, one way of approaching that is to use the replica trick. So first you compute trace row to the n for every value n, and then you analytically continue in n to close to n equals 1 to compute the von Neumann entropy S minus trace row log rho. So the boundary conditions for trace row to the n are shown here for the case n equals 6. These black lines are asymptotically ADS boundaries, and the dashed lines mean that the flavor indices at the end of the world branes at the ends of each segment should be the same. So the completely disconnected geometry, which is analogous to one of the two terms we considered before, just has 6 of these disconnected disk-like geometries. And there's also, at the other extreme end, there's a completely connected geometry, which all of the different 6 asymptotic boundaries are connected by bulk geometry. But clearly there can be things intermediate between the two. And in order to compute this thing at arbitrary values of little n, and to analytically continue, we're going to have to somehow understand how to treat geometries with arbitrary degrees of connection and disconnection between the different boundaries. So to analyze that problem, a nice simplification is to use this limit we discussed a second ago, where e to the s and k are both very large, but with some fixed ratio between them. And in that limit, only planar geometries, like the one at the left, contribute. Things with handles on them don't contribute, as we discussed a moment ago. And although it's a little bit less obvious, crossed geometries, like the one shown at right, also do not contribute. Only planar things, like the one at the left, contribute. But you still have to sum up all of them, all possible degrees of connection and disconnection. And I'm not going to go through this in detail. I just want to show you the idea of like the trick that makes it possible to analyze that sum, because I think it's kind of cool. And this is something that Zhenbin Yang really figured out how to do. So the first step is rather than trying to compute trace row to the n, for the purposes of analytic continuation, it's actually convenient to compute this thing called the resolvent. It's like a generating function for all powers of rho to the n. So it's a sum over all powers of rho to the n, of 1 over lambda to the n plus 1 times rho to the n. And the boundary conditions for this resolvent quantity are shown in the next line. Different terms in the sum. So the n equals 0 term is the first one. That's just delta ij. The n equals 1 term, we have 1 copy of rho, so this is just rho, right? This is the boundary conditions for rho. It has 1 asymptotically ADS segment, and then 2 places that it intersects into the world branes. Then for the rho squared term, we have 2 asymptotically ADS boundaries, and so on. So the sum of planar diagrams for this resolvent, we can fill these boundary conditions in different ways. For the first one, there's really only one way of filling it in. But for the second term here with two asymptotic boundaries, we can either have a disconnected geometry or a connected one. And the basic tool is that this sum of planar diagrams can be obtained by a Feynman diagram. It's like a Schwinger-Dyson equation that says that the sum of all diagrams on the left-hand side can be represented in terms of the sum of all diagrams on the right-hand side. And these Feynman diagram relations are difficult to process in real time, but if you sit down and think about it for a moment, you'll see that this is a correct equation, and it gives you a closed equation for the resolvent R. And that's basically enough to get going, to compute the resolvent, and from that thing to compute the von Neumann entropy. And it does lead to a function that's basically a smoothed out version of the minimum of log k and the Bekenstein-Hawking entropy of the black hole. So it reproduces this, this page curve for the entropy of the system R. Okay. Okay, so at this point I'm done with entropy, and I was thinking of moving on to discuss another aspect of this PETS map thing, but does anybody want to ask any questions about this entropy stuff? Okay, well, in the last few minutes, I'll just discuss this PETS map thing. So the question here is, is the following. If K is very large, then it's expected that by acting on the radiation system R, it should be possible to control the region behind the horizon where the end of the world brains live. In particular, there should be operators that act only on the radiation system R that create or destroy quanta behind the horizon of the black hole. So that's a way of saying that for the evaporating black hole, at very late times, when a lot of radiation has come out, you should be able to learn about the interior of the black hole by just looking at the radiation. Or, you know, if somebody fell into the black hole, you should be able to read the state of their diary by looking at the Hawking radiation, or you should be able to create a particle behind the horizon by looking at the Hawking radiation. So we'd like to understand how that works in this model. So, okay, so so the question we want to address is how we can act on the radiation system R to create a particle behind the horizon of the black hole. And in order to have some particle that we can imagine creating, we have to enrich the model a little bit to have a propagating field in addition to these end-of-the-world brains. And so now we can consider states of the black hole where the end-of-the-world brain is in some state I, like we've been saying so far, but we also have some general state A for the quantum fields propagating on the background. So this cat vector psi I comma A represents a state of the bulk where we have an end-of-the-world brain, this blue line here, in state I. And we've also inserted some kind of source on the asymptotic boundary to create some particles in the bulk. So the state of the bulk fields is state A. So I labels the state of the end of the world brain, and A is some general state of the bulk fields. And to make this discussion as simple as possible, we're going to focus on just two different states, call them 0 and 1. 0 is very much like what we've discussed so far. It's an entangled sum of psi I comma 0, so that's the black hole with no particle behind the horizon, and with end of the world brain in state I, this state vector here, entangled with the reference system in state I. So this dashed line here represents the reference system, and here's the black hole with no particle behind the horizon. To represent these states, I took this half moon geometry, Euclidean geometry, and cut it in half to represent the bulk state here. Okay, and the other state we'll consider is 1, which is a state with one particle behind the horizon, otherwise identical. It's an entangled sum with the end of the world brain in state I, and the reference system in state I, and also one particle behind the horizon. So here are our two states, 0 and 1. They differ in that there's a particle behind the horizon in state 1 and vacuum in state 0. Okay, and what we would like to do is act on the radiation R and somehow turn state 0 into state 1. So that's the concrete problem. And the tool for doing this is something called the PETS map. And I'm only going to explain a sort of baby version of this that Steve Schenker coined the term PETS light for. And it works for a certain class of states, fixed area states of Akers, Rath, Dong, Harlow, and Maroff. I'll explain that in a moment. Actually, I probably won't explain it too much, but don't worry too much about this fixed area restriction. So We would like to find an operator acting on the system R that turns state 0 into state 1. And, well, an example of an operator that would do that would be the expression that I wrote here, but without this trace over B and without the constant C0. So if you ignore the factors that I highlighted in blue, then this is clearly an operator that turns state 0 into state 1. But it's not an operator that acts only on the system R. So as an incredibly naive guess, what you could do is you could start with your formula that definitely works. That's this 1, 0 dyad, and just take the trace over B of that operator. That will give something that acts in system R. Whether it has anything like the desired properties is unclear at this point. And we can also include a normalization factor C0, which we could adjust later. Okay, so if you take the states in the previous slide, 0 and 1, and you write out this formula here, you find the expression C0 over K times the sum over I and J of this stuff on the right-hand side. So that's a maybe naive, but a candidate operator. It acts in the system R, and we're hoping that it's going to take state 0 into state 1. So to check if it works, what we would like to do is compute a matrix element of this operator between two states, A and B, where A and B could individually either be 0 or 1. And if you write out that matrix element using the formula for the operator on the previous line, you find the expression written here. And the thing I want to draw your attention to is that it is a product of two inner products between these psi states. And by now, we're great at evaluating products of inner products of these psi states. And in particular, we understand that there are two kinds of geometries that can contribute. A product of two disks or a connected geometry. And in the case where K is very large, much larger than e to the s, so that's in the region where the connected geometry dominates, then the computation of this matrix element will be given by a geometry that's shown down here on the left. So it will be a connected geometry. And I apologize for this because this fixed area state thing is kind of annoying, and it's just the way it is. So this PETS light map that we're discussing is a special case of the PETS map of a general reconstruction formalism that works for what are called fixed area states. What a fixed area state is, this is something that was discussed by Akers, Rath, Dong, Harlow, and Marolf. And what it is a bulk state where there's one point in the geometry here where you fix the area, or you fix the value of the dilaton, JT graphing, and you allow arbitrary conical excesses or deficits. And in particular, when we connect two geometries together, we allow a 4 pi total conical angle around that point. So this connected geometry that I drew here with a 4 pi conical angle around that point is actually the geometry shown at right. It's two copies of the standard half moon diagram that have been glued together, cut and then glued together, so that these black dots here are conical singularities with total angle 4 pi. Okay, so I don't know if that was clear at all, but the geometry at the right here, after gluing these two cuts together, becomes the geometry at the left with a conical singularity in the center with angle 4 pi. And this is the geometry that dominates the computation of this product of matrix elements. So here's the point. The point is that these two copies, these two asymptotic boundaries here, represent two replicas in this computation. They represent the two factors in the matrix element of the operator. The first factor is the one I'm showing with my cursor now. That's the actual physical copy of the black hole. Those are the ket and bra vectors in the states A and B. The second copy here is associated with this factor here, which is in the operator OR. So, can you hear me?
We can hear you, yes.
Great. So there's two copies of this.
We have to leave. Thank you, Douglas. We have to leave.
Okay, okay, bye. This one represents the physical black hole, and this other one represents the formula for the operator. And when we compute the matrix element of the operator OR, one finds that these two copies are connected by a replica wormhole. So the physical black hole gets connected by a wormhole to a fictitious copy of the black hole in the quantum computer that you're using to act on the radiation. And that connection, that wormhole connection, acts as precisely a creation operator behind the horizon. If you think about this physical black hole here, what we've done to attach the wormholes, we've cut behind the horizon, and we've inserted this geometry here, where the particle propagates from the boundary of the fictitious copy in the quantum computer to the region behind the horizon, and then it comes out in the physical black hole. So the wormhole that connects the physical black hole to the quantum computer effectively acts as a creation operator behind the horizon of the physical black hole. Okay, so I won't go on to discuss the full PETS version of this operator, but that's just a way of relaxing this fixed area restriction. So sorry for going a couple minutes over time. I'll stop here. Thanks for your attention.
Thanks. Any questions? Do feel free. Okay. If there's no questions, then let's thank Douglas again. Thank you.